Hi guys. Due to this coronavirus outbreak, many companies have started using AI for discovering new drugs. Being a data scientist, I have made this small tutorial for anyone who wants to contribute to this field. This tutorial is based on a paper titled Junction Tree Variational AutoEncoder for Molecular Graph Generation, which is authored by Dr. Wingong Jin, and the link to the paper and Git repo for this implementation is shared in the description. Along with this, I have also shared some good resources for those who would love to understand the math behind it. So let's get started. For those who don't know what a variational autoencoder is, let me give a short introduction. It's an encoder-decoder pair, but unlike autoencoders, in which encoder just encodes the data into a compressed representation and decoder tries to regenerate the original data from this compressed representation, in variational autoencoder, the encoder learns the distribution of the input data, essentially the mean and standard deviation of the compressed representation. Now the first question may arise that what are the advantages of this variational autoencoder? The answer is, as the decoder is trained on a distribution rather than individual representations, so if we sample any random point, we can generate a totally new data point not present in the input set but has similar properties. So essentially, we can use this concept to generate new molecules. Now let's talk about junction tree variational autoencoders. In this type of variational autoencoder, each molecule is treated as a tree with each node corresponding to a functional group, ring or atom. So this method is better than treating a molecule as a graph, because if we consider a functional group as a node compared to an atom, we can avoid intermediate invalid molecule generation, as you can see in this image. So after we train our variational autoencoder, we can sample new molecules from the latent space, which looks like this. As you can see, when you traverse this latent space, the adjacent molecules are similar. That is, only a single functional group is added, or the bonding atom has changed, or a new ring has formed. So we can say that the adjacent molecules are structurally similar with minor changes in its properties due to different functional groups. Please mind that the variational autoencoder I used has 56 dimensions, and in this diagram I have just changed 2 dimensions, keeping others constant. Now what if the molecules we sampled from such a vast latent space shows inadequate properties? For instance, what if you need molecules with higher log P, synthetic accessibility and rings? So how can you get better molecules from this variational autoencoder? Rather, how can you choose those samples from the latent space which can generate better molecules? This can be done using Bayesian optimization, which optimizes the sampling function and samples the latent space from areas it believes shows better properties. So using this, we can generate molecules which are better than the ones we trained the variational autoencoder with. For the tutorial, you can just clone the Git repo and open the tutorial notebook, which contains the whole pipeline from training till sampling and Bayesian optimization. For training, you will need an input dataset of molecules in SMILES format. SMILES, or Simplified Molecular Input Line Entry System, is a string representation of a molecule which is created following certain rules and is quite useful for deep learning projects. I have used Ring dataset for training, and the whole trained model is already pushed on the Git repo. Please play with it. So using this VAE, I both generated new molecules and used Bayesian optimization on the dataset to get molecules with better properties. For proper perspective, let's check out this image. For the properties in input dataset, we can reach a maximum value of 4. And as we sample randomly, we could only reach a maximum value of 2. But when we use Bayesian optimization, we reached a whopping 10 in the sampled dataset. With this, I will conclude this video. I hope you liked it, and let's fight this virus with AI as a weapon. Thank you.